Example 1. Given f of x equals 2x cubed minus 6x plus 5, find the intervals on which f is increasing and decreasing. Find the local maximum and minimum values of f, and find the intervals of concavity and inflection points. So, first off, it's very important that we understand where things are coming from. So, intervals of increase and decrease and local maximum and minimum values are all about the first derivative. F prime of x establishes all that information. So when I'm answering that type of question, and again, where I'm going with this is I want to be able to graph things. What I need to be able to do is establish what's going to help me find what they're asking me to find. So this is going to be just a typical thing when you're graphing. You want to find increase, decrease intervals, and you also want to find maximum and minimum values of f. All right, you want to find that stuff. That's all about the first derivative. The second thing they ask us for, intervals of concavity and inflection point, that's all about the second derivative. Oops. What I'm writing here, f prime of x. All right, second derivative, f double prime of x. There we go. Keep writing enough stuff up there, the right thing will go eventually. So, f double prime of x. So, the blue stuff has to be done, and then once I'm done doing all the blue stuff, then I want to move on to the red stuff. Eventually, I want to use the first and second derivative. For me personally, what I do is I go ahead and find f prime of x equals something, which is, in this case, 6x squared minus 6. And I go ahead and find f double prime immediately, because I'm going to have to find it also. Might as well know what it is. Before I start messing around with anything, I just go ahead and find both the first and second derivative, because as soon as they start asking for concavity and inflection points, second derivative comes into play. So knowing what it is useful. So I would probably do that first immediately on any problem I'm going to graph. Go ahead and find the first derivative, find the second derivative. And then when I'm doing stuff, I need to know what to go back to refer to find out what I'm looking for. So for part A, they want intervals on which f is increasing and decreasing. To do that, I have to find critical numbers of the first derivative. Critical numbers of the first derivative occur at endpoints. We don't have any. Where the function is undefined or the derivative is undefined, that's a polynomial, it's never undefined. And where the derivative equals 0. So the only thing we'll have to consider here is where does the derivative equal 0. So I go 6x squared minus 6 equals 0. Again, I referred back to my first derivative because increasing and decreasing has to do with that. So that's all I care about right now. Since there is no x to the first term, I can solve this by moving the 6 to the other side. Divide by 6, we get x squared equals 1. We take the square root, we get x equals plus or minus 1. Be very cautious. If you're going to go without factoring, make sure that you remember that x squared equals, you're going to get a plus and minus number there. If it said x squared equals negative 1, there isn't one, right? So then there wouldn't be any change. It would always be positive or always be negative at that point. So if there's no critical numbers, there's no critical numbers. That happens sometimes. These are critical numbers of the first derivative. And what that tells me is something happens at 1 and negative 1 that might be important enough to investigate further. All right? As far as answering question A, if I want intervals of increase and decrease, I'm going to go from negative infinity to the smallest critical number, from the smallest critical number to the next biggest, and so on until I get to the biggest, which I've already gotten to, and then from there to infinity. Create intervals from negative infinity, stopping at every single critical number in numerical order. However many critical numbers you have, in this case 2, you should get exactly one more interval from that. So, in this case, 3 intervals. And at this point, I want to establish whether the graph itself is going to be increasing or decreasing on these intervals. What I'm considering is, when will this function be positive or negative based on these intervals? Okay, we know it equals 0 exactly at 1 and negative 1, right? So that means it's either positive or negative everywhere else. And the sign won't change until it hits one of these numbers. So whatever sign it is at negative 500, it's the same sign at negative 2 and negative 3 and negative 4. Once I hit negative 1, though, I'm allowed to change sign, right? So I just have to pick a number on the interval, pick a number on the interval, pick a number on the interval. And I'm going back to the derivative to evaluate that to find out what kind of sign I get for each of these situations. So if I put negative 2 in place of x, I'm going to get positive 4 times 6 is 24 minus 6 is 18. That's positive. Put 0 in, 0 times 6 is 0 minus 6 is negative. Put 2 in, 4 times 6 is 24 minus 6 is 18, which is positive. So I know for a fact right now, before I do anything else, this graph increases from negative infinity to negative 1, this graph here. From negative infinity to negative 1, this graph's going up. Then it flattens out. From negative 1 to 1, it goes down. Then it flattens out. From 1 to infinity, it goes up. So without it doing anything else, that's what the graph looks like. It goes up till it gets to -1, then it flattens out, then it goes down till it gets to +1, then it flattens out, then it goes up. Goes up, goes down, goes up. 0, flattens out. Alright? So again, I haven't done anything more than just find two numbers, and I've already got basically what the graph looks like. Pretty helpful. As far as what they're asking us for part A, I'm going to just write my answers here. Increasing would be -infinity to -1 union with 1 infinity. When there's multiple sets, just put a little union symbol. And then decreasing, it's only decreasing from -1 to 1. Also in part B, I can go ahead and answer that right away. It says find the local maximum and minimum values of f. Alright, so again, we know it goes up, flattens out, goes down, flattens out, goes up. So I know this is a maximum, right? Local. This is a local minimum. Again, just based on what's happening to the graph, it goes up, flattens out, goes down, goes up, whatever. I can see with my own eyes, if I just kind of sketch what it kind of looked like, local max, local min. The local max is happening at x equals -1, min's happening at x equals +1. I don't have to draw the picture, just know increase, decrease, increase. If it switches from increase to decrease, it's going to be a maximum. If it switches from decrease to increase, it's going to be a minimum. Again, the picture is not required, just get an idea of the meaning between the increase and decreasing intervals and maximum and minimum values. So I know it's going to have a local max of something at x equals -1, and it's going to have a local minimum of something at x equals +1. How do I determine the somethings?
Look at the graph.
Okay, but where would I go on this page in order to find out the specific numbers I want to put there?
Your original function.
Original function. I'm trying to graph this. We're always trying to graph this, okay? The derivatives are helping us find information about that graph, but if we want to find out exact values of places that things are happening, the exact y values, we're going back to f of x every time. So I need to do f of -1 and f of +1 to find these two numbers here. My calculator is smart enough to know that, and it's nice enough to tell us 2. So 2x cubed minus 6x plus 5. And if I type in -1 and +1, I've got 9 and 1. That's everything the first derivative is going to tell me, ever. When's it increasing, when's it decreasing, what's the maximum, what's the minimum? That's what the first derivative answers for me on a graph. Once I've found that information, now I want to move on to the second derivative. I'm going to do a similar task with the second derivative. I want to find critical numbers of the second derivative. Critical numbers of the second derivative happen at endpoints. They happen when the second derivative is undefined, and they happen when the second derivative equals 0. Sound familiar? Same criteria, right? There are no endpoints. 12x is never undefined, right? And it equals 0 when x equals 0. All right, so I can see the critical number of f double prime of x with my own eyes is x equals 0. That's just a basic algebra equation. 12x equals 0, x equals 0. I believe you did that in your head. Okay, hopefully you believe I did it in my head. So what I'm going to do here is I'm going to set up intervals. I'm going to go from -infinity to what? 0, and then from 0 to infinity. There's one critical number, we get two intervals. Again, the derivative itself equals 0 at x equals 0. That means it doesn't equal 0 anywhere else, which means it's either positive or negative. We have to establish its sign on each of these intervals. The sign only can change at 0, so from -infinity to 0, some sign is going to stay the same. From 0 to infinity, it's going to be some sign that's going to stay the same. I'm going to pick a number on each interval, picking -1 and 1. You can pick -37 and 25 if you feel like it. I pick small numbers myself, but as long as they're within this interval, pick a number between 0 and infinity. 33. Okay, that's play that game. You know, I'm thinking of a number between 1 and 10. 5, wrong. Right? I'm thinking of a number between 0 and infinity. Anybody?
75 million.
It was 7.27. Good try though. All right. Anyway. It's really tough when you have infinity numbers. But again, pick a number on the interval. That's all it is. It doesn't matter what these two numbers are as long as this number is within that range, this number is within that range. And we're going to put these numbers x in place of f prime to determine the sign. 12 times negative 1 is negative 12. 12 times positive 1 is positive 12. This number itself is not as important as the sign. I can see that the graph is going to be concave down from negative infinity to 0. It's going to be concave up from 0 to infinity. And it switches concavity not at an asymptote, because again, this is a polynomial function. There are no asymptotes. It switches concavity at 0. That means 0 is going to be an inflection point. Okay, that's all you have to do to establish an inflection point. If the concavity switches and there's no asymptotes around, then it's an inflection point. So, for part C, it said identify the intervals of concavity and inflection points. Concave up, 0 to infinity. Concave down, negative infinity to 0. Inflection point, 0 comma something. If I put 0 in place of f of x, what do I get? If I put 0 in there, what do I get? 5. Inflection point 0, 5. So as far as what they asked me to do, there you go. I found everything they asked me to find without using a graph. I used a sketch to get a visual of this, but again, I can do that without a sketch. Increase to decrease is a maximum, decrease to increase is a minimum. Okay? I figured out 3 specific points on this graph. Negative 1, 9, 1, 1, and 0, 5 are 3 points on the graph, right? So now if I went to a piece of graph paper, using all the information I just determined, it was above the x-axis. I had negative 1, 9. Oops, I didn't put it far enough down. All right. 1, 2, 3, 4, 5, 6, 7, 8, 9. That's a local maximum, right? 0, 5, 1, 2, 3, 4, 5 is an inflection point, and 1, 1 is a local minimum. Okay? The graph increases to here, turns around, decreases to there, turns around, increases to there, right? This is an inflection point, this is a local max, this is the local minimum, right? And if I were to connect the dots with the proper concavity, concave down, concave up, it's concave down from negative infinity to here, so I'm going to make it go like this. And it's concave up from here to infinity, so it's going to make it look like that. My guess is that's pretty much what the graph looks like. I went to my calculator now and went on a window from negative 2 to 2, because that's all I've got really right there, right? And let's go from 0 to 10, hit graph and see. It's basically the same shape. Reason mine's a little squishier is because I've got more space here, right? Spread out more. So if I actually were, let's say, to go from negative 5 to 5, then you get more of the picture I found. All right? Again, I found 3 points. That's all I found. My graph looks very much like the correct graph, right? That's the idea. We're using calculus to minimize the number of points needed in order to make a very detailed, correct graph without having to find 5,000 points to make it happen.